Now can you hear me? Fine. So let's start. I have to pause this. Yes. Hope all of you are well, and welcome to the live session for Multiprocessor Architecture Part 3. First of all, I will like to tell you one thing. For the purpose of attendance, what you have to do is just write down your name and university roll number into the chat box so that I came to know whom of you are actually attending the live sessions. Uh, and now let's get to the topic. Hope you have gone through the previous tutorials of multiprocessor architecture. If you have gone through those two tutorials, until now you have learned about what multiprocessor architectures are as a whole, what is NUMA, COMA, and UMA model, then what is cache coherence and consistency problem, and how to solve those using Snoopy bus protocol and directory based protocol. Now, at the heart of the multiprocessor architecture, as you may have noticed, is the interconnection network, if you can remember. So, just as a quick recap, this is the general structure of a multiprocessor architecture where you have n number of processors are there into your CPU. Then you might have local memory adjacent to individual processors, as well as you might have centralized shared memory with the processors. Now all the processors actually communicate with one another using the interconnection network. Today we are going to study different facets of interconnection network and a few types of them. So just before diving deeper, have a look at a few diagrams. Say this green circles are your processors. Now in this interconnection state, you can see that each processor is connected with one another. So in that sense, we can say that this is a completely connected network where each and every processor is connected with one another directly. That means, let for the time being we name the processors P1, P2, processor P3, processor P4, processor P5, processor P6. Now you can see that if processor P2 for the time being, if wants to communicate with processor P5, it can do it directly. It doesn't have to go through via any intermediary. So uh, give it a thought and try to figure out what can be the advantage of this kind of interconnection network. And what can be the disadvantage? If you can figure out any disadvantage, write it in the chat box. And let's we move to the next diagram. Yes, this type of internetworking is termed as shared bus network. Now, what is a shared bus? Shared bus, also called common bus, is a simple type of static network actually. Now, if you look into this diagram, you can figure out that different processors can communicate with one another through a common bus. Now, whenever say processor P1 has to send some message to other processor, what it will do? It will actually throw a message into this shared bus mentioning the address for the other processor to which it wants to make a communication. And then come to this next diagram. Here you can see that different processors are connected with one another as a ring. As the look of the diagram suggests, the name of this kind of network is called ring network. Here each and every processor is connected to its adjacent processor only. Now then you have a tree-like structure also. You can connect different processors into your CPU as a tree. Yes, Dhiraj. He has written disadvantage, speed of communication will be slow and cost will be more in implementing this type of network. Advantage, high speed communication. Correct. Yes, just let me for a moment go back to this diagram. You can see that as different processors are connected to one another directly, so the communication speed will obviously be higher. However, if you can look into the implementation of this kind of network, it is going to be complicated. So high cost is a factor here, and speed of the communication will be slow because the algorithm will be more complex. Okay, so you can implement your interconnection network using tree-like structure. Then this is a hypercube structure. You can see basically in this implementation the processors are fabricated in a three-dimensional way. Okay, fine. So this was basically a brief overview of different kinds of topologies following which you can fabricate your multiprocessor interconnection network. Now let me do some deeper dive. Now networks interconnection networks can be static or dynamic. First, we will look into static networks. Static networks will mainly be characterized by their node degree. Now, what is node degree? Node degree basically represents the number of links connected to each node. For example, say you have a node A which is directly connected to other two different nodes, say node B and node C. In this case, the degree of node A is, can you please tell? If you can figure it out, write it into the chat box. I will pause for a second here. Yes, as you can see, the number of edges which are directly connected to node A are 2. So the degree of node A is 2. Similarly, the degree of node B is 1 because there is only one edge connected to node B. Similarly, for node C, the degree is 1 because the number of edges connected to node C is 1. So, depending on the degrees, you can classify the interconnection network topologies which we have observed a few moments before into different categories. As for example, shared bus network has degree of 1. Then if your network follows linear array or ring topology, then its degree is going to be 2. Binary tree. Binary tree means, roughly speaking, where a node has exactly 2 children. Binary tree can have degree 3. Is this correct? Fat tree, shuffle exchange, then degree 4. Two-dimensional mesh, iliac. We will look into this today itself. Then varying degree, n cube, n dimensional mesh, k array, n cube, binary tree, and so on. Just let me look into them one by one. Some examples which we have observed before. Then look into this linear array network. In linear array network, what happens? You can see that most of the nodes has degree 2. Why? Just as an example, look at processor N1. It is directly connected to two other processors. So the degree of N1 is 2. The linear array has each node connected with 2 neighbors. However, we have 2 exceptions here where the degree of the nodes are not 2. Can you figure those nodes into this diagram? If you can figure them out, write down into the chat box. I repeat the question. Look into the linear array network. Try to find out the nodes which don't have 2 as their degrees. Node 0 and node 3. Right. So, universally, you cannot say that always linear array network will have 2 as its degree. Some of the salient features might be, uh, you can say that all the nodes basically share a common communication link because of its linear nature. And as you can see, why this structure is linear? Because N0 and N3, that means terminal nodes, are not connected to one another. They have degree 1. So it looks like a linear array actually. Um, so other problems which might arise here is there can be long communication delays here. For example, how we can justify this? Say node N1, processor N1 wants to communicate with N0 or N2. Then they can directly communicate with one another. In those cases, communication delay will be smaller. However, say if N0 wants to communicate with N3, what will happen is then the communication has to hop through the intermediary nodes. So depending on their situation or their state at that particular moment, there might be longer communication delays. Then come to the next structure. This is a binary tree network. So, sorry, hope you might have studied binary tree in your maths subject. This top node is called the root node. And in such a network, what usually happens is each intermediary node has two children. If you look into our diagram, N2 and N3 are intermediary nodes. You can see that both of them has exactly two children. Now, how to address them, or more precisely, how to assign address to them? The root node has address 1. The root node has address 1. And the address of the children of a node are obtained by appending 0 and 1 to the node. That is, if the address of a node is x, then its left child will have 2x as its address and right child will have 2x plus 1 as address. So if you follow this convention, this is the address for left child and this is the address for right child. If the address of root node N1 is 1, then you can see that the address for the left child of root node will be 2. That means 2 into x, 2 into 1, 2. And address for the right child will be 2x plus 1. That means 2 multiplied with 1 plus 1. That means it is going to be 3. Now try to find out the addresses of the left and right children of node N2. The address for node N2 is 2. So the address of its left child, that is N4, is going to be 2 multiplied with 2, that means 4. So its address is 4. And address of its right child is going to be 2 into 2 plus 1, that is 5. And similarly, you can figure out the addresses for N6 and N7 respectively. Uh, so you can see that the routing algorithm here will be much simple. However, can you figure out one problem in this zones? The communication channels near the root will be always busy with respect to the communication channels near to the terminal nodes. Why? Because say right subtree and left subtree processors want to communicate with each other. In all the cases, the communications have to be done via these channels only. So you need higher bandwidth requirement here. To compensate that problem, basically fat tree network has been proposed. So one problem with the binary tree is that there can be heavy traffic flow toward the root node. And to solve that problem, fat tree network has been proposed. If you can see into the diagram of the fat tree, you can see that the number of communication channels near the root are higher than the number of communication channels near the terminal nodes. And this has been done to handle the heavy traffic towards the root node. And next, yes, you can have ring interconnection network. In this case also, uh, you can see that the degree of each and every node is basically 2. Yes, I will come to this later on. Apart from this, there can be uh, let me take one page here. Yes, hypercube network. And hypercube networks are basically of three-dimensional structure. You can see a hypercube network here. Sorry. And these are your nodes or processors. Now, for the time being, observe this hypercube network and tell me what is going to be the degree of a node. Write down into the chat box. Yes, hypercube network has degree 3 for each node. You can see that each node is connected to three different nodes directly. Say this is node A. It is directly connected to node B, node C, and node D. So its degree is basically 3. Now, depending on the discussions that we have done, networks can be either blocking or non-blocking. Let me show you the definition. I hope it is here. Yes. So have a look into the definitions. A network is non-blocking if it is capable of connecting an unused input to an unused output, no matter what other connections are being used in the network. A network is blocking otherwise. To get sense from this definition, let me go back to our previous diagrams. So this can be an example of, no, this, not this. This can be an example of blocking network actually. How? Say there are single communication channels in each edge has been implemented. So, and this is your root node. Say this is root. And for the time being, this node A and this node B is making communication among themselves. So their communication channel or communication path is going to be something like this. So for the time being, you can say that node A and node B, processor A and processor B are busy. However, other nodes are free. They are doing nothing for the time being. So can you please tell, say here you have node C and here you have node D. Although they are free, can they communicate with one another at the same time while A and B are making communication with one another? Write into the chat box. Yes, right. Dheeraj has written no. And the answer is correct. They cannot communicate with one another as the communication channel itself is blocked due to its implementation structure. So now I think this blocking and non-blocking concept makes sense to you. Before looking into the example once again, let me look at an example for non-blocking network. Yes, this is an example of non-blocking interconnection network. Say P1 and P4 are making communication with one another at a particular time instance T. Now, at the same time instance, P2 and P5 are not doing anything. So if they think now we want to communicate with one another, they can obviously do, because their communication channel is not blocked by any other communication channel. Now have a look at the definitions of blocking and non-blocking. Once again, a network is non-blocking if it is capable of connecting an unused input to an unused output, no matter what other connections are being used in the network for that particular time. Now, it is non-blocking. Two unused inputs can communicate with one another no matter what other nodes are communicating with one another at that particular time. So this is non-blocking. The definition is justified, and a network is blocking otherwise, as we have looked into the tree example. Now, this blocking and non-blocking concept can be thought in other way also. A blocking network is rearrangeably non-blocking if once the permutation from inputs to outputs is known. Now, what is the justification behind this statement? To look into the justification, let us look into the ring connection. If you look into the ring connection, for the time being, say processor P1 is communicating with processor P3, and this is processor P2, P4, P5 and P6. Our assumption is that processor P1 is communicating with processor P3. So if you carefully look into the diagram, processor P1 cannot directly communicate with processor P3. Either they has to follow this route via P2, or they has to follow this route via P6, P5, P4. So for the time being, let us assume that they are following this P2 route. So this channel is free. Now at this particular time, if processor P6 wants to make communication with processor P4, they are free to do this. Processor P6 can communicate with processor P4 via node P5. So in that sense, what happens? You can notice that this topology becomes non-blocking. However, say processor P2 wants to communicate with processor P6. Now, will it going to happen or not? Write the answer into the chat box. I will pause here for a moment. Now you can see that in this particular case, processor P2 cannot communicate with processor P6, because to effectively communicate with P6, P2 has to hop via P1 or via P3. However, at that time instance, P1 and P3 both have been occupied by some communication data. They are doing some communication among themselves. So in this scenario, what will happen? This topology becomes blocking. Repeat the question. Okay, the question was that while P1 and P3 are communicating with one another, can P2 communicate with P6 at the same time? Or in other words, say at some time instance, P1 is communicating with P3. On that time instance, some necessity have been arrived that P2 has to communicate with P6. Can P2 communicate with P6? I hope the question is clear now. If you look into the situation when P1 and P3 are communicating with one another, P2 cannot communicate with P6 because they will block the communication path, and at that time this network becomes blocking. So you can see that a network can act as a blocking as well as non-blocking network at different time instances. So this was the essence of this discussion. So there are different types of networks which are implemented in the real scenario. Some are 2D mesh, then you will have shuffle exchange network, you will have to study butterfly network, then yes, for today we will look into the 2D mesh-like network structure. So what is a 2D mesh network? Just look into the definition. It is a two-dimensional network. In this, all processing elements are arranged in a two-dimensional grid. If you look into this diagram, this looks like a two-dimensional if you look into this diagram, they are fabricated as a two-dimensional grid. The processor in rows I and column J are denoted by Pij. As for example, this is your processor 00, this is processor 01, processor 02, processor 0n, and so on. So if you look into this grid-like structure, you can see that for a particular node, the maximum degree which is possible is 4. If you look into the middle of the grid-like structure, say PE11, you can see that there are 4 edges connected to this. So in that case, its degree becomes 4. Now, just pause for a second, give yourself some thought and try to figure out a particular processor can communicate with which other processors. I repeat the question once again. Say you have a particular processor into this structure, say this one. Can you find out in generalized terms with which other processors a particular processor can communicate with? Just give it some thought and try to figure out the result. Okay, if you look into the diagram carefully, you can find that a processor can communicate with its adjacent left and right processor and adjacent upper and lower processor. Say processor P11. Its adjacent left and right processors are PE10 and PE12, and adjacent upper and lower processors are PE01 and PE21 respectively. They can directly communicate with uh, these four processors. However, connection is possible between all the processors for this PE11, but direct connection is possible only with these four processors. Depending on these assumptions, there something has been implemented in the past, and the example is iliac network. It looks something like this. Here, rather than two subscripts, the processors, yes, someone has written, Saket has written with neighbor's processor. Yes, you are right. In this grid-like structure, a processor can directly communicate with its left, right, upper and lower neighbors. Now, let me come to the example. An example of this mesh network is iliac network. Here, the processors has been assigned some numbers from left to right rather than two subscripts ij. The upper left processor is assigned number 0, then 1, then 2, then 3, then 4, 5, 6, 7, 8, 9, 10, 11, and so on. So the idea behind this numbering or this implementation was to algorithmically or mathematically formulate something by which the system can tell with which other processors, uh, where is it? It is not here. Which other processors the processor can directly communicate with. Yes, just look into the formulations, and the formulations look like there must be brackets here. So J is the number for the processor, and N is the total number of processor. This is a 16 processor architecture for this particular example. So N in this case is 16. For the time being, say we want to calculate with which other processor 5 can make direct communications. Let me put them into the formulas. If you look into the first line, now it is for processor 4, what you have to do, you have to write 5 in place of J, then add 1 to 8, then mod 16, and the result is going to be 6 modulo 16 equals to 6. You can see that processor 5 can directly communicate with processor 6. By following this first formula, you arrived at this conclusion. Now let me find out the other processors by following the formulas. Next formula goes like J minus 1 modulo n. That means 5 minus 1 modulo 16, and it is 4. You can see that processor 5 can directly communicate with processor 4. Now This conclusion we have got by following this second formula. Now let me try the third formula, which goes like iliac plus nj equals to j plus n mod n. Now I am not being able to. Now try to put this into work. 5 plus 4 mod 16, which gives you 9. So you can see that processor 5 can directly communicate with processor 9. One thing which I have not mentioned yet is small n. It is basically square root of big N, which in our case is 4. So you have arrived at this conclusion by following this formula. Now let's try the last one. And the last one goes like 5 minus 4 modulo 16, and it gives you 1. You can see that processor 5 can again directly make communication with processor 1, and this conclusion we arrived by following this formula. So this was all about this iliac network example. Hope you have been able to uh, grab the concepts for the day. One thing I will like to say is that whenever you watch this kind of online tutorials, always keep a notebook and pen with you and jot down the points, whatever you think important, and later on give them your thought. If you find something difficult, then rewind the video and watch that particular portion once again. And another thing is that if you have not gone through the previous tutorials for this module, before watching this tutorial once again, at first study those tutorials, then come back to this video once again. In this way, I think you can get a sound understanding of this multiprocessor architecture. Hope you have learned something. Have a good day. And if any one of you have not yet written his roll number into the chat box, kindly do this right now, as I am going to disconnect within some moment. Okay. Have a good day. Thank you.